elements here, first 3 elements here, first 2 elements, or, well, middle 2 elements. Is everybody kind of comfortable with that? Any questions, feel free to ask, because it's just, fundamental stuff. If you're comfortable with lists, just move on. Dictionaries are like lists, except instead of being indexed by a number, they can be indexed by an object, such as a string. So in this example, we're defining a dictionary, and notice the difference is curly brackets instead of those straight brackets. And we just put a string for like someone's name and maybe like a score or something. So we have this list of people and scores. And then this is one way of constructing a dictionary. And then we can add an element to the dictionary like this. We put a new element with the key of Henry equal to 66.1. There. And you can print stuff out. Here. This is how we reference elements in the dictionary. Okay? What's up?
I tried to modify the print x minus 3 colon nothing.
Yeah.
It would be different.
Broke?
With case back something.
Yeah, because x is defined up in the earlier thing. So unfortunately, you gotta go and you gotta
I have to
execute that, and then
okay.
yeah. So if you're having errors, if you reference x down here, x is actually defined in cells that are above this. So you actually have to execute those cells first, and then go down, which is kind of frustrating.
I'm going to copy and paste and put it in a new box.
Whatever you want to do. Yeah, Sage is not perfect by any means, but it's good
At
enough.
least we know how to hack it.
Yeah. Do whatever you have to do to make Sage work, and if you have any questions, let me know. I had to deal with this. Somebody used Sage for a class I took, a really good class at UC Davis, and I spent probably 6 months using it. And it's very frustrating. But if you want to put LaTeX and Python and text and stuff all in one document, it's not bad. I mean, there's not a lot of other stuff out there that does it. There's IPython Notebook, and Sage is actually based on IPython Notebook, so there's really only one kind of player in the game, I think. So, iterations. If we have lists of things, we usually need to iterate through them and do stuff with them. So, say we want to sum up all the numbers in X. We start with, we define a variable equal to 0, we go through each element in X, and we add to this variable. It starts out as 0. And in the end, we wind up with the sum of all the elements that are in the list called X. This for loop, very fundamental. In any language, there's not much more you can say about it. I mean, you gotta learn your for loops if you don't already. I'm sure many people do. If you want to iterate through a dictionary, the keys and values in the dictionary in Python, you do for, and then these are the values you're going to iterate over, or this is the values that you get when you iterate, I should say. And then you call, D is a dictionary, you call this iteritems function. So you can iterate through each key value pair in the dictionary. So, and then we're going to print some stuff out here. So we just print out the names of people and their scores.
So iteritems is just a basic part of the dictionary type in Python. Okay.
It's a function of the dictionary. It returns an iterator object, I think.
Okay.
And then anything that returns an iterator object can be iterated over with a for loop.
Okay.
So, is everybody comfortable at this point? Okay. So, we can sort lists in Python relatively easily. If X is a list, we can print what X is beforehand, it's this guy, and then print it after. We can just call the sort function of X. And something to note about this is that it's going to sort X. It's going to sort the numbers within X. It's going to use the memory that X takes up. It's an in-place sorting method. So whatever x was before, it's going to be changed. It's going to have the sorted elements in it. So x before sort is this, x after sort is this. It's a list of sorted numbers. And we can do the same thing with y. It will alphabetically sort things. We can do reverse alphabetical order, saying y dot sort and saying reverse equals true. And here's the array before, and here's the array in reverse alphabetical order afterwards. So if your sorting is nice for when you're you got to print something out and you're just doing some preliminary data analysis and you got to just look at your stuff, make sense of it. List comprehensions are really cool. They're kind of like shorthand for you can basically the idea is you have a list and you want to do some operation on the elements of that list and get another list out of it that's the same size. So say I wanted to square all of the elements within X. Well, I can write it in this really compact way. The double star is the exponentiation operator, so it's like, val squared. So I can do an iteration through X here, and then this is my variable that I get out of each iteration, and I can square it. And then I construct a new list. So the result of this is a new list. So we print X beforehand, and then we print X squared, this variable X squared, and obviously we get all the values squared. And list comprehension just, I find them pretty cool. They feel good until ready. And if we are importing this operator package, and operator has a lot of different stuff in it. I'm just going to use it for one purpose here. First thing I'm going to do is I need to sort a dictionary. But I can't really sort a dictionary. So I first turn it into a list. So I iterate through each key value pair in the list, and I put it in this, or in the dictionary, and I put it in a list. And each element of this list is a tuple. A tuple is like a list, except you can't write to it. You can't change it. And then I sort this list, and then I pass the key argument to the sort, which basically says get the second element of this list and sort on that second element. So I have this list of tuples, these key value pairs. The first value is a name, the second value is a score. And I'm sorting the list by the score, because the score is the second element of each tuple. And I'm doing that through this operator class. Is everybody comfortable with that enough? Or? And if you had objects, for example, just an aside, like if you wanted to sort a list of objects, instead of using item getter, you use attr getter, ATTR, and you can get, if you have a list of objects and you have a property that you want to sort on, you can use attr getter. I don't know how people would say that. I've never actually heard this.
So the argument to item getter, you're telling it to sort on the value? Is this the second thing in the tuple?
Second element.
Second element in the tuple?
Yes, this is an index.
All right.
Yeah, index. And attr getter, you pass a string, which is like the name of the property that you want to sort on.
Okay.
Just make sure everybody knows to count from 0.
Yeah.
Always index starting from 0, unless you're in MATLAB.
Or Fortran.
Fortran.
I know.
Yeah. Well, if you're in Python, start from 0.
So, operator. Could you explain just briefly about what operator is?
Operator is literally a file with a bunch of functions in it.
Okay.
It's
a library.
Yeah, it's a library.
Okay.
It comes with Python. There's a lot of packages within Python. We're just importing that package, and we're just referring to a function within that package.
Okay.
Python's a little, I used to use Java, right? Like Python's a little flatter than Java, whereas Java will have pretty deep packaging.
Yeah.
Python's not.
Just one name.
Shallow in terms of its packaging.
How does item getter know what you're sorting? How are you passing the list to item getter? Does it?
You're passing item getter, whatever that is, its object, to the sort function.
Oh.
The sort function is actually an
Is
member
calling something
variable
that's.
of the list.
I got you.
So we're sorting the list in place using
Right.
its own function called sort.
Right.
And we're passing the item
Operator.
getter as an argument to the sort function.
Okay.
there's an alternate, if you don't want to do in-place sorting, there's a function called sorted, S-O-R-T-E-D, that you can call on the list, and it won't do in-place sorting, it won't modify the list itself, in case you're concerned about that kind of stuff. So we have this list here, and it's a list of tuples, and so we can refer to both elements, in every iteration, and we can just print them out, and you can see here that they're sorted by score. And keep in mind, we're not iterating over a dictionary here. We took the dictionary, we turned it into a list, we sorted that list, and we're just printing it out.
So once you print that list out, then you put it into a tuple?
It was, so we took tuples in this list comprehension. So what this is doing, this is saying, we're gonna go through every key value pair in this dictionary called D, right? And we're just gonna put them together in this tuple. This is how you define a tuple, right? And then, so there's gonna be this is a list comprehension, so the result of this is going to be a list. This is a list of tuples. And each tuple has the name and the score in it. And then we're gonna sort that list here, and that's where the operator stuff comes in. We get the score, which is the second element of the tuple. And that's why we pass index 1 in there. And so it'll sort that list based on that value.
Can you show how to initialize the dictionary?
Yeah, I'll write it down because I don't think this is editable. If I just want to define a dictionary without anything in it, I just say like D equals dict. An alternate way is to just have curly braces. If I want to put stuff in it, I'll just say key value, where these are objects or whatever, strings. This would have to be a string or something, but whatever, or variable. But yeah, that's 3 different ways of defining a dictionary.
Okay. So this would be a constructor like in C++, or?
This? Yeah.
It's like that?
Yeah, it's exactly like a constructor. I think dict is a class.
Oh.
Yeah, Python's pretty object oriented. Okay, so that was my brief introduction to lists and dictionaries and sorting and list comprehensions in Python. Is everybody comfortable with that? Comfortable enough? Okay. So NumPy arrays. The question is, well, can we do better? If we have all these great data structures in Python, do we need anything more? And the answer is, yeah, probably. Because we want to do things like take 2 lists of numbers and add them together, or like without using a list comprehension, maybe square all the elements in the list, or add functions so that we can compute the mean of a list of numbers. And we want to do matrix vector multiplication. We're not going to do that today, but there's a lot of stuff that we want to do with lists of numbers, and we need a more sophisticated data structure to do that. So that's where NumPy comes in. The first thing we need to do is import NumPy. And this is how I usually write code. There's other ways to import NumPy so that you don't need to prefix everything with NP, just to, give you a heads up. It's just the way I write code, so if it bothers you, this is not, you don't have to do it this way.
So you can use NumPy's namespace.
Yes.
Okay.
Like I always explicitly use namespaces. I don't like to import star from the package and then just, use things willy-nilly.
Gotcha.
So first thing I'm going to do is I'm going to take a Python list of numbers here, and I'm going to wrap it in an array object. This is a constructor, this is an object. We're constructing an object, an array object. We're passing it a list of numbers. And then I'm just going to print it out, and it's down here, and it just looks like a list of numbers or something special. What's special is what we can then do to it. So if I just want to add 5 to everything in the list, I just do x plus 5. And it'll broadcast that 5 to every element of the list and just add 5 to it. If I want to multiply everything by 2, I just say 2 times x. If I want to square every element, I do x double star square. If I want to compute the mean of a vector or array, I'm going to use the words vector and array interchangeably. I can just do that, or I'm sorry, mean. If I want to compute the mean, I just call the mean function. If if I want to compute the standard deviation of a bunch of numbers, I can do that very easily. If I just want to sum a bunch of numbers within an array, I can do that very easily as well. There's a ton of other stuff that is defined both within the array class and outside of the array class for operating on arrays that makes NumPy very useful for manipulating lists of numbers. And those are just some examples here. So one thing that's super powerful in Python when you have an array is you can index certain elements of the array and do stuff with them. For instance, say I wanted to find all the negative numbers in the array I just constructed. Then I just do this. I say neg index is equal to x less than or equal to 0. And before I go to the next couple lines, it's important to understand what this object is. What is this variable? Now, this variable, when you do some expression like this, is called a logical expression. When you take an array and you apply a logical expression to it, this is a binary array. It's an array of true and false values of the same length as x. So just to write an example on the board, say x is equal to 2, -4, 3, and I say x, and I say y is equal to x less than 0. What y actually becomes equal to is false, true, false. And this is a NumPy array. So we can wrap that in a NumPy array. But this logical indexing gives you a binary vector that you can index stuff into. So if I say x, y here, where y is an index, it's going to give me basically -4. And that's what happens here. So I can call sum. If I call sum on a binary vector, it's going to add up all of true. And false is equal to 0, true is equal to 1. It's like universally true in language. So if I sum this array, it's going to give me the number of truths in the array. So if I sum this index here, it's going to give me the number of negative elements. So if I just say negindex times sum, it gives me the number of elements in this vector x that are less than 0. And let's see here, if I index the original array with this logical index here, and go down here, where is it? It's here. It will give me like a shortened array with just the elements that I'm looking for. So indexing is super powerful. You know, I can't stress that enough. Like, you should always use logical indexing, because a binary vector takes up a lot less space for one reason. You don't want, like, an alternative to this would be to get the indices that represent all of the elements in x that are less than 0, for example. Much more expensive memory-wise. If you have a gigantic array, like, we want a logical index. You want something that's binary because it takes up a lot less space than the actual indices that you're looking for. So for another example here, we just look at all the elements in x that are greater than 0. And what we do is we sum them all up. So we look at x and we say, this is the index I defined here. All of the elements that are greater than 3, and then sum them. And then it just prints it out here. The value is 130 if you want to check it. X was equal to this. It's like 3.1 plus 22.7 plus 99.1 should give you 130? No? I think there's 5 and 1 you gotta add those into. You can check it later. No, my check it later. Another thing that you might want to do pretty often is take two arrays and multiply them element-wise. They call it element-wise multiplication, where you take each individual element of the array and you multiply them together, and then you produce a new array. So if I make a new array called y, that's the same length as x, different elements, and I print x, print y, I can just sum them up individually. This is element-wise addition. or I could multiply them. This is element-wise multiplication. There's a lot of stuff you can do to two different ratios. You can divide them, you can do whatever you want. And the reason that you would want to do something like this, instead of using like a for loop, is because NumPy, when you compile it on your machine, like on an Intel processor or something like that, it will become optimized to do vector operations on the processor. So when you do element-wise multiplication, it will actually automatically parallelize some of the stuff that you do. So it's always better to take, if you're going to work with a bunch of numbers, in NumPy, to turn them into arrays or matrices, multiply them that way, instead of doing it with a for loop. And yeah.
That's specifically in NumPy, or you're saying more in general, or like what? Like,
I would say in NumPy.
NumPy.
NumPy can be optimized so that when you do vector operations, it uses instructions on the processor that will speed that up and parallelize some of it. So it's typically better, I shouldn't say always, it's typically better to do element-wise multiplications through vectors and matrices instead of doing for loops.
So in Python, you would have to do like a map or zipper, or zip kind of operation on it to do
Mhm.
that same thing?
To sum up the elements.
Well, I guess,
Yeah, in this case you do this for loop, but yeah, if you want to, yeah, you can zip. Fine. I still find myself zipping once in a while, but usually not for this kind of stuff. If anybody's not familiar with zip, zip will take two arrays and it will return an iterator. So I could do something like for x val, y val in zip x, y here, and make a for loop out of it, and then I can say, actually I can just do a list comprehension. It'd be like x plus y, or something like that. So this would be equivalent to creating, or to just, this whole line is equivalent to x plus y here. And I'm sorry, this should be x val plus y val. So I could do this in this list comprehension and it would return a list, but there's no reason to, once you're using NumPy, there's no reason to keep doing that. Is that cool? And one more operation that you will probably come across in your machine learning endeavors is a dot product. The dot product, if I take two arrays, say, the dot product is literally just equal to 3 times 1 plus 4 times 2 plus 5 times 4, so it's like 3 plus 5 times 4 is whatever that is. So the dot product is pretty commonly used for a lot of different stuff. And this is how you call it. So the dot product of x and y, and you print it out. It's literally just equal to x times y and then the sum of that. The element-wise multiplication of the sum, so that you have the same number. It's just good to know that that function exists for now. If we start talking about matrices, we won't today, but if we start talking about matrices and vectors and matrix vector multiplication, I tend to use dot a lot. There's alternatives to that, but when we talk about matrices,
Can X or Y be on several dimensions?
that's if X is a two-dimensional thing, if it's an array, you can say X times Y. You can do NP dot matrix times vector, and it'll return a vector. So if you need to do linear algebra, you can use NP dot. But there's also a matrix object in NumPy, and you don't need to use NP dot when you're a matrix object. I never use matrix objects. I'm not sure if I'm missing out or what. I always use dot.
Wait, but will it add 0? Like if X has is 4 dimensions and y is, 2, we'll just add them so you can get it, or is it
I don't think so, I think it'll just fail. You can
Let's
try
just
that.
I'll try right now.
Yeah, try it out.
Oh wait, and can X just be an ordinary list, or does it have to be an NP array?
I don't know, some Python function, or some NumPy functions will work with lists just as they'll work with arrays, like any iterable object.
Alright, I'll let you guys know.
Okay.
Well, the X in here is the pre-NumPy X, right? So it's in the.
No, it's an
Not
upgrade,
really.
right?
Anyway, no.
No, it doesn't,
So
dimensions
that,
matter.
so now, no, it doesn't work if it's just lists.
Oh, okay.
So now I'll make it NP array and then make it different.
So something I think that like people are gonna do more and more over the next decades is generate a lot of random numbers all the time, for all sorts of things. There's a conference that happens every year called NIPS, it stands for Neural Information Processing Systems, and there was a whole workshop on just random methods for doing machine learning. For instance, if you want to do compression, you have a vector, like a list of numbers, and it's a big list, and you want to compress it, you can just multiply it by a random matrix that reduces it to a smaller amount of dimensions, and then you can use an algorithm later to decompress it, not even knowing what matrix you use to compress it. And that's a whole field that's kind of exploded in the past 10 years called compressed sensing. Yeah, another use of random numbers is like when you construct a neural network. These days, if you construct what they call a deep network, part of constructing a network is taking data, adding random noise to it, and then fitting your algorithm with the input that all noised up in different ways, and just fitting it over and over again with this noisy data. And so that the network learns how to, predict things better, learns how to generalize better, noisier data. So random numbers are very important, and it's important to know how to use them. So first, we generate 4 types of random numbers. The first type is a uniform random number. So it's a uniform random number is a number between 0 and 1, equal probability of being any number, any decimal between 0 and 1. And you can do that saying numpy random.rand and then pass it 5, and it's going to generate a 5-dimensional array, or length 5 array of uniform random numbers. If we want to generate random integers, we can do that with the randint function. So any numbers between 0 and 9, and then 5 of them. So it generates them here. Random binary numbers are really just a subset of random integers in some ways. So I call randint again, and just go from 0 to 1. You always put 1 more than you want to generate here, and then generate 5 of them. So I get 5 binary numbers. And then Gaussian random numbers, also called normal random numbers. Gaussian and normal distributions are the same thing. And that is the randn function. We can generate 5 of those. The Gaussian curve, there's actually a plot of that at the bottom, so we'll talk more about that. So yeah, random numbers, that's how you generate them. Do it for fun. And plotting. So there's another package. It's complementary to NumPy and SciPy, which I haven't even mentioned SciPy, but NumPy and SciPy, they're 2 very closely related packages. NumPy kind of provides like the guts for doing mathematical stuff, and SciPy has all these more advanced computational things, like a Fourier transform or something, for example. Matplotlib is another complementary library that is for plotting all kinds of stuff. So in this example, scientists discovered the number of people that buy ice cream from a truck is always twice the temperature, as long as the temperature is between 70 and 90 degrees. So we're going to create that data. We're going to create a plot that illustrates that ice cream demand based on temperature. Crucial thing. especially with all this talk of global warming and all that. You know, very important. So we define an array temperature, and we're using a new function here called arange, which takes the start and the end of the array, and then the spacing between the elements. So it generates a bunch of elements between 70 and 91, spaced by 0.5. And then we generate the ice cream sales, because the scientists found that ice cream sales are twice the temperature. So we just multiply 2 times the temperature. And then we're going to create a figure for it. So you figure, and then we plot, here's the core kind of thing here. We plot the temperature, this is the first array, versus ice cream sales. And then this is the format string. This K means black, and this dash means a line. It's going to connect all the points on that line. We give it some labels. We make sure the axis is tight so that there's no like weird, space at the end of it. And then this is just a Sage thing, right? When you save the figure here, you can call this, when you're just working in IPython or just a command line, and it'll save the figure to the file system. I actually have to do this because we're using Sage. So, just so you know. This is what that plot looks like. It's a straight line. Here's the temperature, goes from 70 to 90, 90.5. And then here are ice cream sales. I just imagine them to be unitless. I don't know. Maybe 180 ice cream sales for maximum on a 90-degree day, which is pretty good. I mean, if you're in a truck and you even have 180 ice creams to sell, I never ran an ice cream truck. But, it's good to know. So if...
No question.
What's that?
I took away the dash, but it's still a straight line.
You got rid of the dash and it's still a straight line?
I mean, I deleted K dash, but it's not us.
You probably defaulted dash. You can put an O in the string, just an O, by a K-O, and it should be dots. It should be like a scatter plot kind of dots.
Yay!
The star is
True
way cooler.
facts.
Oh, good.
Look at the star.
Yeah, yeah.
And there's other letters you can use, G and for green and R and B and all that stuff. Or you can pass it HTML color codes, and not through that string, but through a different variable. This is a different plot. This is like if we wanted to, we found that the relationship between ice cream sales and temperature is different at lower temperatures. It's equal to the square root of the temperature between 10 and 70. We can make a plot of that. We can construct these arrays. And so, this is good to know because if the curve was linear, right, if this was just a straight line, if you took the scientist's first model and you said, oh, well, I'm going to extrapolate this to lower temperatures, and you just thought it was a straight line, you would totally be buying too much ice cream at low temperatures. So it's important to know when and why you're extrapolating when you read some results of stuff, because it's not always going to work. Things are very non-linear. And I think that's it for the ice cream example and the plotting. Is everybody okay with the plotting stuff? I mean, it's a huge thing. There's tons of stuff you can plot and all kinds of different functions for it. This is just the start. This is the basics.
Just pushing it tight, the block
Tight.
axis tight makes.
I like to do that obsessively. Because sometimes I'll plot stuff and then it'll extend out to 70, but the curve will stop there. It's just really annoying.
So I remove it and it does.
Yeah, that's what it does. I hate that. Yeah.
So instead of that, you just tighten it to the.
Yeah, just tighten it and it brings the axis in. Right. I don't know what the criteria is for that. It drives me nuts. I mean, it doesn't make me, because it doesn't keep me awake at night, but
Okay, that's good.
So, one last thing for the NumPy, SciPy, or Matplotlib tutorial is distributions and histograms. What I mean when I say distributions is if you have a whole bunch of numbers, they have certain frequencies to them, 10 might appear a bunch of times, whereas 2 might appear almost never. So numbers are distributed in a certain way. And we want to, when you get a data set and you have a set of numbers in your data set, you wanna know the range of those numbers, and you don't wanna just know their maximum and their minimum and their mean. You wanna know where they fall, like how many, you know, like, if you're doing something like, you have an online game and you wanna see like, you know, how long do people play for, and you want a distribution of that. You know, you could use a histogram to plot that. So, in this example, we're gonna generate 5,000 random numbers. Hopefully it won't be too taxing for the server to do that, I can't imagine it would be. And we're gonna use the hist command. So grands, or grands, is like a bunch of Gaussian random numbers. And they fall, the average of these random numbers, and we generate them as 0, and the standard deviation is 1. And we're going to do a histogram of that, and we're going to make 20 bins. If you increase the bin size, it's going to be a finer curve in the histogram. And we're going to give it any color of red, and the next label, and a Y label. And we're going to save it. We're going to like this. Kind of like a bell curve, which is what a Gaussian distribution is all about. But yeah,
So a normal random would be flat.
our uniform
The uniform.
random number will be flat across here.
Yeah, so this is Gaussian and
This is Gaussian.
the uniform would be flat.
Uniform is flat. What's that?
I don't know.
That's perfect.
I like asked it for 50, and then I wanted to see the error when I put in 51, and then I did that, and now it's here. Because 51 should give an error, right? So it's like, I only generated 50 numbers. And now it's good.
Maybe that'd be weird, but yeah, I mean, it's sparsely sampled because you generated 50 random numbers.
No, but like 51 bins with only 50.
It'll still work. It's just,
Why would it work?
well, because it's just binning things. Like if there's nothing to go in the bin, it's just 0. So let me explain this a little more. The x-axis in this histogram
Yeah.
is any number that could occur within the set that you give it. So the maximum and minimum in the set that I gave this is probably somewhere around -4 and 4. So it's going to use those as the boundaries. And then it's going to separate this into 20 bins because I passed the 20. And then each bin starts out with a count of 0. And then I get the first number in the array, and I'm like, oh, well, that's 2.5. I'm going to put it in this bin. So on and so forth. So if there's not enough, if things don't fall in the bin, it'll just stay 0. But it won't break. Okay? Is everybody comfortable with this? You feel free to play around with this for a couple minutes if you want, and then we can move on to the next tutorial. I'm just going to sit down for a second, make some water. Go to the bathroom, so.
If it takes some time, it's because we're asking to generate a random number.